So let's have a look at the model then. This time, actually this first quiz could work for both last time and this time actually. But this time we need to be slightly more detailed. We need one more thing. Now here's the formal linear model expressing sort of the basis for the analysis that we do. It looks a bit like a regression model, and somehow it is, but we express it slightly different and more directly here, in that we say we need, like last time, we need the double index to index the groups and index the individual observations within groups. They come with an overall mean. They come with a contribution for each treatment, exactly like last time. So the model sort of anticipates in the outset that the three different TV sets could have different levels of sharpness. It's a friendly model, doesn't make any strong assumptions. It puts those sort of details of the world that we'd like to investigate, they are put into the model for us to be able to investigate them. That's kind of the idea of statistical models. That's to express those phenomenon that we'd like to actually zoom in on and get information about. That's the idea of a model, to be explicit about how we filter the world, how we look at the world. That's what we put into the model expression. But then the new thing today is that there are also some persons or some blocks, and blocks could be different also. And whereas a few weeks ago we got rid of this term by differencing, we could do that when there are only two. Then we can just take the difference. It's not an approach when there are more than two. So we have to do it a little more technical way. We need to express explicitly that some blocks might be at a high level, other blocks might be at a lower level. That's the beta j here, expressing that. Then, apart from that, still, we have random variability. That's the residual variability, which we have the, by now, usual assumption for all the linear models and ANOVA regression models we've been doing in this course. We assume normality and the same variance all over, the same residual variance all over. It's a non-trivial assumption, for sure, but it's the classical basic assumption of these models. Yeah, that's basically it. It's not too difficult to compute what those numbers should be if we wanted to estimate all those elements of this model. That's also a way to see it. That's what we do in regression models, right? We have the model and then we estimate the intercept and the slopes to sort of quantify what are the elements of this unknown model. Well, it's the straightforward thing that anyone, any third grader I'm sorry if I offend anyone by saying that, but I'm pretty sure if we ask third graders to actually solve this challenge, they would solve it the right way, not knowing anything about analysis of variance or stats in any way, because what am I showing you in this slide? I'm just showing, why don't we take the mean of those three, 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 and then I take the mean of those four, the mean of those four, and the mean of those four, right? I take the mean for each row and the mean for each column. I mean, anyone could have gotten that idea. If they should summarize what's going on, I would claim anyone would do that. And that's just what I'm putting on this slide. I'm saying, let's take one set of the means here, the other set of the means. These are row means, column means. Then I take the overall mean, and then just to make them model express deviances, I subtract the overall mean from those specific row and column means, and that would be the estimates of those contributions expressed in the model. So it's kind of, it's just in a way complicating simple means considerations that anyone would have anyway. But it's not only complicating, it's of course formalizing this into a framework that we could move on from here, right? To three-way, four-way, multi-way, all sorts of generalizations in the same way of expressing things. That's the neat thing about this approach here. It doesn't only give you some tools here and now, it also gives you the possibility to build on top of those tools later in your life and in your career. It could be, it's difficult to see, but these are just hand versions of these means, just the overall mean, and then I use this t-apply to get the treatment means, and just straightforward mean calculations. So nothing in a way dramatic in that. That was the basic means. That this is the whole purpose of the analysis of variance, to investigate those means. It's not rocket science, it's just simple looking at those means and trying to make sense of them, right? It's nothing more than that. So, let's see how that helped out. You ready? Well, most of you are okay. Some of you are still struggling a little bit here. This was a repeat question, right? I was referring back to last week, one way and over. The residual variability, that's the within group variability. And roughly, the average within group, the average spread of the dots here in the two data sets are more or less the same, right? The difference we see is between the groups, not within the groups, right? There's a difference between the between group variability and the within group variability, which this question was supposed to make you realize and think about. Some number there is doing well. And then I should remember this now.